So first of all, what I want to consider is what happens when you have two masses that are pulling on each other or pushing on each other that are accelerating. We've already done one problem of this on the homework where you had a guy pulling his sister in a wagon. And so, but now we'll do something different. All right, let's suppose we have the following situation where we have, let's just do an example, where we have two masses. M1 is equal to, and we'll put in numbers, 10 kilograms, and M2 is 20 kilograms. Okay? And let's suppose that you have somebody pushing on these masses, and this whole thing accelerates with an acceleration A in the x direction is equal to 2 meters per second squared. All right. Let's go ahead and see if we can figure out the force, normal force on the mass, on mass 2 by mass 1. Okay, let's find normal force, how much mass 1 pushes on mass 2. So let's go ahead and do this example. I'm going to do everything algebraically that I can, and then at the end I'll plug in numbers. We can assume for now the frictionless. So maybe these are on wheels or something like that where friction is not important. And hopefully this will illustrate what we want to cover. The main thing that you want to do on these is to draw a free body diagram for each mass separately. You really don't want to get confused by trying to do everything at once. So I'm just going to draw a free body diagram for mass 1. What are the forces on it?
The person.
Yeah, okay, you have the force by the person. Let's call this FP. For the force due to the person. What other forces?
The force of the mass 2.
Yeah, so if mass 1 is pushing on mass 2, mass 2 has to be pushing back on mass 1, right? Mm-hmm. So let's go ahead and do normal force on mass 1 by mass 2. Okay. So notation on by, I'm putting an N here for normal force. All right, what other forces? Okay, we have weight downwards. I'm going to introduce another notation just because I like this notation. To write like mg for the weight, okay? Put a little vector on here indicating that this is a vector. Okay, M1 downwards, okay. Anything else? You have a normal force upwards. All right. Anything else? Very good. That is all the forces that are on here. Yeah, in the absence of friction. All right. What do we do now?
Draw a body diagram for the other one or not?
Well, we could, or we could just we could start applying Newton's second law to this particular mass. How do we do that?
FMA.
Yeah, sum up all the forces. It's going to be equal to MA. Okay. So this is a vector equation. So you can look at the x and y components, but first we've got to define a coordinate system. But how do we want to do that? Yeah, let's do the normal one. So that's the usual coordinate system. And so how do we, if I want to say sum up forces in the x direction, what should I do?
If the
Forces in
normal
x.
force.
What would it be?
The normal force of 1 by 2.
So, like that?
Force P minus normal force of 1 by 2.
Yeah, so if I want to do just the components in the x direction, the force by the person is in the positive x direction, right? All of it is. So this is how much of it's in the positive x direction.
Minus
And then what else is along the x coordinates?
the normal force by 1. I mean 1 on by 2.
So should I do like this?
No, minus.
Okay, so it points in the negative x direction. All of it does. So I will put a little minus sign on here, write it like that, okay? And what's that equal to?
MA.
M, the vector A?
A in X direction.
Yeah, that's right. This is the x part of, this has an x equation and a y equation. It's really two equations if you write it like this. So we have an x equation like this, right? And what mass should this be? M1. M1, because we're just looking at the free body diagram for M1. All right? So, we know neither the force of the person nor the normal force, right? But we do know this stuff. So this is one equation. We don't have enough information yet to figure out everything. So, what we do is we look at the second equation, right? How do we get a second equation?
Total force. Oh, do we need to? Yeah.
Well, that will tell us some things, but, I mean, that'll just tell us, well, okay, let's do the sum of forces in the y direction. Let's see what it tells us. What are the forces in the y direction?
Normal force minus mg.
Normal force minus m1g, and that's equal to what?
MAY.
And what's the acceleration in the y direction?
0.
0. Okay, good. So what did this tell us?
Normal force is equal to the weight force.
Yeah.
Good. That might be important if you have friction. This friction will be related to this, it'll be proportional to this normal force. So you need to do that if you have friction. But it really doesn't, it's not going to tell me either of these things, so. So that's not quite where we want to go. What we want to do is we want to look at the free body diagram for mass 2 and get equations from that, right? So if I do that for mass 2, what forces do I have on mass 2?
Normal force going up.
Normal force going up, fine.
Force on 2 by 1.
That way?
Yes.
Yes. All right, normal force on 2 by 1. Right? So this force and this force will be third law pairs. Anything else?
The entry.
All right, M2G down. Good. So, yep. So what should I, so now what do I do?
Sum up the force. Oh, introduce a coordinate system.
Okay, good. This way, maybe I want to introduce a coordinate system like that, right? Does that a bad coordinate system?
Yeah.
Useless coordinate system. All right, let's do it like this. Good. So what's the sum of forces in the x direction?
Yeah.
So normal force on 2 by 1, and that has to equal what?
MA. Oh, yeah.
And what's m?
MAX. Oh,
M?
what's M?
2.
Mass.
Second mass, right?
Oh,
Because
yeah.
we're just looking at the second mass,
AX.
AX. All right, by the way, this N21, the magnitude of it, is that the same as the magnitude of this one? Yes, by Newton's third law, those forces are equal in magnitude, just opposite in direction. So when I put these bars on here, that means magnitude. I'm not interested in the direction of that. So I just figured out what N21 is. Here, okay, that's one equation. So so I can take, and this is going to be equal to the same thing as the normal force on 1 by 2 because of Newton's third law. That the force, yeah, that they'll be equal but in opposite direction, equal in magnitude. So I can take this and plug it into here, can't I? Well, actually, this is just what I wanted. I don't have to do anything more, right? So, for instance, let's plug in numbers. So M2 was 20 kilograms, right? Times in the acceleration, meters per second squared. Which is 40 newtons. You guys follow that? All right. Let's see if let's say I wanted, so A, we just found this. 40 newtons. Let's say I wanted to get what the force that the person exerted is on that box. Could you do that now? All right, B. Find force person exerts. Or magnitude of the force. Go ahead, see if you can get that real quick, okay? Give you about what's that? That's 40 newtons, right? That was at N12. So how much is it?
Shoot.
60. All right. You got it?
See this thing? Do you know this number already? This number, M1, this one,
Yeah.
that's 40 newtons. Okay. Then you have the M1AX. So you know every number here of this thing.
Oh, that would be MG.
All right. You ready? What did everyone get? 16 newtons. All right, let's see how we did that real quick. So you took this value for N12, which was 40 newtons. You plug it right into here. So this is where FP is, that's what we're looking for. So I know everything in there but one term, so I can solve for this. So I get that the magnitude of the force that the person exerts is N1AX plus N12 was M2 AX, right? From over here. By the way, this is just M1 plus M2 times the acceleration in the x direction, as you would expect, because you can kind of think of it as one person pushing all the mass at once. And then this would be 30 kilograms times 2 meters per second squared, which is 60 newtons. And of course, there's many other ways to do this. You could have just put in 40 newtons here, assume that this was 20 newtons through there as well. Okay? Make sense? All right, but the key thing for these two mass systems, you consider a free body diagram for each of the masses separately, and then do Newton's second law for each of the free body diagrams. Does that make sense? Then you'll get what you need to get. We've got another problem for you related to that. All right, one of the things that comes up quite a bit is pulley systems. And so pulley system, you know, you have a little wheel that's free to rotate, and then you hang a rope over it. Hopefully, maybe from one mass to another mass or something like this. Let me see if I can hang this rope. So say you have something like this, where you have a pulley here, this thing's free to rotate, and a rope that goes over this pulley. So, you know, if I pulled it down like this thing would be going up. Does that make sense? If I pull mass 1 down, mass 2 has to go up at the same rate. If I pull mass 2 down, mass 1 has to go up at the same rate. And then we're going to consider what's known as an ideal pulley. So the ideal pulley has a couple of characteristics. One, this is massless. So we'll find out later that with this being massless, it doesn't have what's called rotational inertia. We won't worry about that now, but it basically means that any force here will have the same force exerted here, okay? So massless and then frictionless. And that there's no friction on this axle here. Okay, ideal pulley. And so all that this does is it redirects forces. So if I have a tension pulling this force upwards, T, and this is at rest, the same tension will be over here. That's what we mean by an ideal pulley. It just redirects the force. And it'd be the same thing, it'd be the same forces as if you had as if I had these two things on a plane with a rope between it, and then having M2G this way and M1G pulling that way. Okay, it's basically the same situation. That makes sense? Yeah, so that's what the ideal pulley does. Just redirects the force without changing its magnitude at all. And so what we'll do, let's see if we can figure out the acceleration of this system or come up with a formula for the acceleration of the system in terms of mass 1 and mass 2. All right. These are both hanging downwards. What's that?
You have a 0 of acceleration, your weights or masses have to be equal.
No, let's say they're not equal.
And you're gonna be moving.
Yes, and accelerating, okay? Let's see if we can come up with the formula for what that acceleration would be. This is a little bit tricky, right? How do we get started on this, do you think? So anytime you want to get started on a force problem,